Okay, so in this video, we're going to look at an introduction to confidence intervals. Okay, so example 1. Suppose the weights of bags of a certain candy is normally distributed with a mean of mu equals 24 ounces and a standard deviation of sigma equals 0.2 ounces. Okay, so the population mean is 24 ounces and the population standard deviation is 0.2 ounces. We're going to take random samples of size 16 taken from the population to form an SDSM. Okay, so this goes back to the previous topics of sampling distributions of sample means. So part A, what would the mean and standard deviation for the SDSM be? Well, remember that the mean of the sample means, okay, mu of x bar, equals the mean of the original distribution. Now that's by using the central limit theorem, and we can apply that here because they tell us that the original population is normally distributed. So that was one of the conditions that we can apply the central limit theorem is if you start with a normal distribution, then the SDSM, the sampling distribution of sample means, will also be normally distributed, and the mean of the sample means will equal the mean of the original distribution, which we know is 24 ounces. The standard deviation of the sample mean distribution will equal sigma over the square root of n, okay, which in our case is 0.2 over the square root of 16, and that gives you a pretty decent decimal value of 0.05. Okay, so that's what sigma of x bar equals, 0.05. Now, notice I didn't round that at all. Okay, that's the exact value. The square root of 16 gives you a nice rational number. So if we want to draw the sampling distribution of sample means, so draw the x bar distribution. Okay, again, this is still going back to the previous topics, and for the sake of time, I already have that done here. So I'm just going to put that up here. We know it's a normal distribution. Okay, so the x bar distribution, okay, we know is normal. And we know that right in the center was 24. And then if you add and subtract that sigma sub x bar 3 times above the mean and 3 times below the mean, okay, it gives you those values on the axes. Okay? So 23.85, 23.90, 23.95, and so on. Okay, so again, there's nothing new there. In terms of looking at z-scores now, for the SDSM, okay, for the sampling distribution of sample means. Okay, so now, one standard deviation above the mean, so a z-score of 1, would have an x bar value, or a sample mean value of 24.05. A z-score of 2 would have an x bar value of 24.10, and so on. Okay, which will be different than saying 24 is in the center of the original, and if the standard deviation was 0.2, then the original distribution would have had 24.2 right here, and 22.4 right here, and so on. Okay, 23.8 would have been one standard deviation below the mean, and so on. Okay, so we can see now we're looking at the x bar distribution, which is essential for the topic we're looking at here. Okay, part C. It says evaluate mu plus or minus sigma of x bar. Well, remember that mu is really the same place as mu sub x bar would be. Okay, so remember that this value here is the mean of the sample means, which is the same thing as mu. Okay? So if we add or subtract the standard deviation one time, we already did that. So we're going to add or subtract 0.05, okay, which was our sigma sub x bar. Subtract it from 24 to get 23.95. Add it to 24 to get 24.05. Okay, so there is an interval that we can form representing the values that are within one standard deviation of the mean. Okay, so any value of x bar between 23.95 and 24.05 are within one standard deviation of the mean. Now, going back to the empirical rule with the normal curve, within one standard deviation of the mean, there is approximately 68% of the data values. So in this case, we're looking at sample means. lie within 1 standard deviation of the mean. So approximately 68% of the sample means lie between 23.95 and 24.05. Okay, and again, this is using the empirical rule. Okay, or the 68, 95, 99.7 rule. Okay, way back in previous content when we did the normal curve. Okay, and then we're going to evaluate mu plus or minus 2 sigma of, sub x bar and mu plus or minus 3 sigma sub x bar. Okay, same idea. We already did those. Okay, those are values up here in the distribution that we already found. Okay, so I'll just uncover that and show the meaning. And if you need to pause the video, go ahead. But again, the 95% and 99.7%, those are coming from the empirical rule that we've already covered. Okay, so moving along for the sake of time, under repeated sampling, okay, which remember, that's what this x-bar distribution is we did repeated samples of size n. In this case, they were size 16. Okay, we took size of 16. We found their mean, or the sample mean for each, and then plotted them on the axes, and ended up with this distribution here. So under that repeated sampling, we see that 95% of the sample means, x bar, will fall between mu plus or minus 2 sigma sub x bar. So we can say the probability that x bar is between mu, or mu sub x bar, minus 2 sigma sub x bar, and mu plus, or mu sub x bar plus 2 sigma sub x bar, because remember, mu and mu sub x bar are the same value. That probability that x bar is between those two values is approximately 95%, or 0.9500. So in our example, approximately 95% of the sample means x bar fall between what two values? And remember, the n was 16 here. If n was a different number, we'd have a different distribution, so you just got to be careful of that. Okay, so 95% are between what we found up here, 23.90 and 24.10. Okay, so there shouldn't be anything too tricky there. Now you may also interpret the results in the following ways. If we take one sample of size n, okay, so if we take one of these samples, in our case it was size 16, we can say that we're 95% confident that our interval, x bar minus 2 sigma sub x bar, to x bar plus 2 sigma sub x bar, will contain the true value of the population mean mu. Now that's a little bit different because up here, we were looking at taking mu, or mu sub x bar, minus 2 sigma sub x bar. Well, now we're just taking x bar and subtracting 2 sigma sub x bar. So that's basically saying now is if you take one of those samples of size 16, rather than taking 2 of them, or 3 of them, or 4 of them, or 10 of them, or 100 of them, if you just take one sample of size n, or in this case 16, we're 95% confident that our interval x bar minus 2 sigma of x bar to x bar plus 2 sigma of x bar will contain the true value of mu. And we'll get into that idea more in the next example here. Okay, another way to interpret that result is if we repeated this process 100 times. That is, we're going to take 100 samples of size n, or size 16, and constructed an interval from each sample mean, then we'd expect 95 of those intervals to contain the true value of the population mean. Okay, so 95 out of 100, we would expect to contain the true value of the population mean. Okay, and if that doesn't make any sense right now, that's okay. When we get to the actual examples, or build on this, hopefully it'll make more sense. Okay, so on the next page here. Now, in practice, we generally don't know what the population mean would be. Okay, so suppose we don't know the population mean of the weights of the bags of candies was 24 ounces. However, we do know that the population standard deviation is sigma equals 0.2. And again, this is not very realistic. Okay, so the concept behind what we're building on here is that we want to be able to estimate what the population mean weight is. Okay, so in part A. So how would you estimate the population mean weight if you didn't know that the population mean weight was 24 ounces? Okay, so what we would do is you'd want to take a sample of size n. Okay, now n in the last example was 16. Okay, n could be 20, it could be 30, it could be 50, it could be 100. Now what you might want to pay attention to with the sample size that you take is you want a large enough sample size for the central limit theorem to apply, because then we're going to be able to use the normal curve. Okay, and that's going to be important for us. So what we do to estimate the population mean weight, if we don't know that it was 24 ounces, you take a sample of size n and apply the CLT, okay, central limit theorem, okay, which was the previous topic, to make an inference or estimate about mu, okay, the population mean. Okay, so if we didn't know the mean weight of the bag was 24 ounces, the best thing you can do is to take a sample of bags of candy, find their mean weights, and then apply the central limit theorem to make an inference about the population mean. So in part B, suppose we take a sample of 30 bags and calculate their mean weight to be 23.96 ounces. Okay, so suppose you go to a store, buy 30 bags of that candy, and you have an apparatus that'll accurately measure the weights, like in a science lab or something. And without actually doing this, although buying 30 bags of candy sounds pretty good to me, okay, you'll buy the 30 bags, find the weight of each, average them together, and we got 23.96. So we want to construct two interval estimates for the population mean. Okay, so let's just do a 95 and we'll do a 99.7 confidence interval. Okay, now again, I already have this stuff worked out just for the sake of time. Okay, but this will be easy to follow along with. Okay, if you want to do a 95% confidence interval, well, you're going to take your sample mean that we found. Okay, again, before it was mu plus or minus 2 sigma sub x bar, but now we don't know what mu was. So now our best guess for mu, for the population mean, our best guess right now is what we found in the sample, 23.96. So we're going to take that sample mean, and we're going to add or subtract 2 sigma sub x bars. So basically we're going to go 2 standard deviations above and below the mean to find our interval. So our sample mean was 23.96. We're going to add or subtract 2. Okay, now that 2 really is like a z-score, because approximately 95% of the values are within 2 standard deviations of the mean. So that 2 is really like a z-score. Times sigma sub x bar, which is 0.2 over the square root of 30. Okay, so sigma over square root of n. Okay, and now when you do those calculations, okay, what I always show is the margin of error, which is the 0.0730, which is 2 times 0.2 over square root of 30. I like to see that number just so you can see what the margin of error is. So 23.96 plus or minus that decimal value will give you 23.887 to 24.033. Okay, so what we're saying is 95% of the sample means would lie between 23.887 and 24.033. Okay, oops, I'm sorry, I just said that wrong. This was x bar plus or minus 2 sigma sub x bar. Let me backtrack. What we're saying is our sample mean has 95% of the values from 23.887 to 24.033. those values are within 2 standard deviations of that sample mean. Okay, so what we're doing here is we're trying to estimate where mu is, or make an inference about mu. So we say that we're 95% confident that mu is contained within this interval, or that our interval contains mu. Okay, another way to write that, okay, is that 23.887 is less than mu is less than 24.033. Okay, so essentially what that's telling us is we have our x bar axes. 24 is going to be somewhere on that axis. Okay, we don't know exactly where it is because we didn't know the mean weight was 24. Okay, but if we were to put 23.887 to 24.033, okay, there's going to be 2 values on the axes, and we can see that 24 is within that interval. So if the mean for the population really were 24 ounces, our interval would support that because 24 is within that interval. Okay, so that interval does contain the true value of mu if mu was really 24 ounces. Okay, on the other hand, if you do the 99.7% confidence interval, well, remember by the empirical rule that was 3 standard deviations within the mean, or I'm sorry, from the mean. So that's like a z-score of 3. Okay, and this is approximate here. So if you take your sample mean and add or subtract 3 standard deviations from the mean of the x-bar distribution, that'll give us a margin of error of 0.1095 and a confidence interval of 23.85 to 24.07. Okay, so notice that our interval got a little bit wider. And I'll explain that later on, why it got wider. Okay, the calculations here are pretty straightforward. Okay, so what that's doing is we're predicting based on 99.7% confidence that the population mean lies between 23.85 and 24.07. So again, on our x-bar distribution, on that axis, the x-bar axis, 24 is somewhere on there, and 23.85 and 24.07 will contain that value of 24. Okay, 24 will be within that interval. So both of those intervals contain mu equals 24. Okay, so now that was all based on taking one sample of size 30, okay, so 30 bags, and calculating this to be their average, 23.96, okay, for x bar. So now suppose you take another sample in part C, another sample of size 30, and calculate its mean to be 24.09. Okay, so now we just end up with a sample mean that was higher than 23.96. So what happens here? Construct 2 interval estimates for the population mean again, and do these estimates contain the true value of mu? Well, if we do the same percent confidence intervals, the 95 and 99.7, okay, if we do those same percentages, okay, the change here is now we're starting at 24.09 for our estimate for x bar. Okay, that's the best guess that we have so far. And now within 2 standard deviations from the mean, so our z-score there was approximately 2 times sigma over square root of n. We get 0.0730. And notice that value, the margin of error is going to stay the same. Okay, and that's one of the interesting things here about looking at the margin of error. When you have the same confidence level, that value in front there, that 2, is the same in each formula, and sigma